forward to the cloud. Hi everybody, it's Ben. This is a video for the differential equations class. This is the fourth try. The subject we're looking at is solving differential equations with discontinuous forcing functions using Laplace transforms. So I'm going to share the screen, I hope. Share the screen, there you go. Yay, Laplace transforms discontinuous forcing functions. Okay, first thing we got to recall is that we have solved a bunch of differential equations previously where they were not homogeneous. We were looking at what to do there when you got this forcing function in there, and we would find the homogeneous portion of the equation by solving L of y equals 0. And then we would try to find the y sub p, which would make that g of t come up. We referred to that as a particular solution. Once you got one of them, then by adding this y sub h, you can get all the possible solutions to the equation, all right? Oh, look, I have iTunes telling me that I need to download something again, and I don't want to. No, I'm going to tell you to cancel, and quit. Okay. Sorry. So the y sub h is the general solution to the homogeneous part, all right? And the g of t that you see over there, a reference that it seems to only be used, nope, I'm not going to say that. It's this reference to a forcing function really makes a lot more sense in the context we're going to look at it here. Okay, so we are going to take a look at a spring system, and the notion here is that you get a spring, which I have drawn the most wonderful picture of ever, and some sort of a weight hanging from the spring, and we take and displace it away from its equilibrium position, and U is what we use to represent that. Now, I am stealing this problem wholesale from another textbook, and it is unfortunate that they use U for that, whereas we are using U for unit step function. So consequently, we are going to be using an H for unit step function, and that's because of the association with John Heaviside, right? Okay, so if we've got this spring system like this and you pull it down and let it go, it will go doing and vibrate up and down. And the displacement of how far it goes up and down, we use the U to represent that. The equation that we look at for this, and in physics class, they would go through the derivation of exactly what's going on with it. But you have this mu double prime. U double prime, of course, is the acceleration of displacement. So you've got mass times acceleration, and we're thinking about forces that are acting on this pendulum that we've got here. So mass is here, and often to figure out what's going on with it, you're going to take a weight that might be given in either pounds or in newtons, and then divide by the appropriate G for your system. And then this gamma here is going to be the coefficient that we think about with the damping force. And so you take a look and it will give you a force divided by velocity. That is to say, it will give you some idea of how much force is happening based on a particular velocity, and then we'll use the gamma as a constant through the equation. And then finally, the K that appears in here is your spring constant, and you find out what that is by stretching your spring. You find some displacement, either stretching or compressing, and you see how much force was used to do that. If you've ever stretched out a spring, you know, as you stretch out farther and farther, it's harder to stretch it out. Whereas when you stretch it just a little bit, you've got a low force. So a small displacement times this constant, and that gives you back the force that you've got, all right? So in any case, you will also have to look at the statement for the problem and see what the u of 0 and u prime of 0 are from the way that it's stated. So our first example here, we've got a 4-pound mass and it stretches the spring by 2 inches. So that piece of information there lets you figure out a couple of things. First of all, that 4 pounds is not mass. That 4 pounds is the force that the mass exerts, its weight. And so we will come down here and figure out that the mass we've got is going to be 4 pounds divided by 32 feet per second squared, that being the g that we use for the old-fashioned imperial system. So then the unit we've got there, 1/8. I am not going to write the units in every piece of this problem because that would just be nightmarish. So, all right, then this other piece that it gives us is that if we are stretching the spring 2 inches, that is 1/6 of a foot, and it took 4 pounds of force to hold it there, that means that the spring constant is 24, okay? Now, the next part says if you've got no damping and no driving force, which means that you have a 0 here for your gamma, a 0 here for your F. Then the equation that we've got, if you want to make it look a little bit nicer, ends up with saying u double prime plus 192u equals 0. So that is an undamped pendulum problem, okay? So then it's a problem that we've solved stuff like it before. We will just write down that we've got r squared plus 192 equals 0. So the r is going to be plus or minus 8√3i. And so our two solutions are going to be cosine or sine of that 8√3 times t. And so our general solution will look like that. We take the derivative of it, you know, the minus 8√3 and the 8√3 come out, and you switch the sine and cosine. But now you can take and plug in to those two things, and you'll find out that your C1 needs to be 1/3, and then your C2 has to be 0. So that says that we've got a u of t being 1/3 cosine of 8√3t. And I just realized that I never said where this 1/3 and 0 come from. The setup here was we stretched the spring 4 inches and then we released it. So in stretching that, we have no, we're not giving it any velocity. It's not like we stretched it and then gave it a push or anything. It's just stretched and released. So that's the reason for the 0 and the 1/3, which is 4 inches is 1/3 of a foot. Okay. So we end up with a solution there of this 1/3 cosine 8√3t. And please realize, no matter what initial conditions that we came up with there, we would end up with some combination of sine and cosine with the same frequency. Okay. But again, undamped pendulum, not super realistic, because if you've got an undamped pendulum, in theory, it goes on going up and down forever. We know that eventually it would stop, but that has to do with how things get damped by dissipating energy one way or another. So, all right, second version of it, right? We've got a 4-pound mass again, so we're still going to get that 1/8. And the medium the system is in gives 6 pounds of resistance for a velocity of 3 feet per second. What the hell, right? What we're referring to here is really something along the lines of a shock absorber. Now, you could have the pendulum that you've got things moving in just having air resistance resisting it there, in which case you wouldn't have very much force opposing the pendulum going up and down. But If instead of air resistance, you set up your pendulum going up and down in water, that would be considerably more resistance. Or molasses, that would be way more resistance, right? Or concrete, that would be ridiculous amount of resistance. But in any case, though, if we've got something that is resisting the direction, then we'll have some statement coming out like this. And you just plug in here, you have to get the units right, that your speed, your velocity needs to be in feet per second if you're going to talk about pounds. And so here we end up with a coefficient being 2 in this. And same thing as before, giving us the 24, so that we get the equation that looks like that. Now, still, we're going to have no driving force in this. So we're going to have the system being compressed. When I said compressed, I was supposed to have something else here, and I did not. Well, let's fix it as we go, all right? But it's somebody compresses the spring and then lets it go. Okay, so again, no velocity. So we've got our equation sitting here, and I prettied it up a little bit by just multiplying everything by 8. And so when we try to figure out the initial equation, we end up with this r squared plus 16r plus 192, which you can use the quadratic formula or complete the square or whatever floats your boat. And you end up with a minus 8 for a real part, and then the plus or minus 8 root 2I for the imaginary part, okay? So that says that our two solutions then are e to the minus 8t cosine 8 root 2t, and then e to the minus 8t sine of 8 root 2t, okay? And C1 and C2, of course. Then if you take the derivative of those in order to try to solve with your initial conditions for what the C1 and C2 are, the derivative will turn out to be this. I don't want to bore you with showing you how that happens, okay? If you're working one of these and you're concerned about checking to make sure that your work is right, one thing that you could do with it is to take a look at some online site like Wolfram Alpha or Symbolab. Symbolab, somebody pointed out to me the other day, does most of the grunt work for what we're needing to do here. Okay, so I was saying here that I'm plugging in, well, maybe I should highlight it like that. I'm plugging in the 0 to the first one, and of course I get C1. And since I wanted to be compressing this at 6 inches per second, but not that I've compressed it 6 inches, but rather that's the speed that I like hit it with, that sets this up, and it means that I don't have it displaced. I've just got a certain speed that I'm going to be shoving it at. So then the other portion of it here is saying that we want to be compressing it at 6 units or 6 inches per second, and that I should have written is a negative 1/2 foot. Since the C1 we know is 0, then the C2 ends up being a negative 1/16 root 2. And so we have that sort of thing there. So you compressed the spring at first, and so you have it, it's going up and down, but it starts with a compression, okay? Now, the one thing to kind of note here is what happens to the solution over time. If I were to draw a quick sketch here of the of what this is doing, it would be maybe, oh, I put it wrong. it would be going between the plus and minus of this exponential here. Okay, the sign is going to make something oscillate, but this e to the minus 8t, because it goes to 0, is going to clamp down or damp the pendulum that we're looking at, and it will go towards 0 as t goes to infinity. Right? Okay, so now we're going to make this do a little bit more. So if you take a look at what I've got set up here, I have the same mass in the same spring. I have the same damping going on with it, but now we're going to have a vibration be added. So the forcing function is just going to be this sine t over here, right? And we knew how to solve these problems already. We can use the solution from the previous page for our homogeneous portion of the solution. But then our particular portion, we're going to say a cosine t plus b sine t. Notice that the root that we would have associated with cosine t and sine t would just be plus or minus I. The root that we had from our initial equation earlier was minus 8 plus or minus 8 root 2 I, which is not the same thing. So we don't have to do anything with adding an extra t in there. Okay, y'all make sure that you understand what's going on with that. The last homework that I was grading the other day, people just kind of put in a t at random, and I worried that you were just doing it blindly without understanding why a t was there. So, okay, anyway though, so if we've got that for our u sub p, then in plugging in the u sub p double prime plus 16 u sub p prime plus 192 u sub p, when we differentiate and put it together, we'll have 191a plus 16b times the cosine, and 191b minus 16a times the sine. So since that's supposed to be equal to 0 cosine t plus 1 sine t, that means that this part has to be 0 and this part has to be 1, and it's just a system to solve there. Okay, I started solving the system and the numbers are ridiculous fractions and they're very small. The A is like 4 10,000ths and the B is like 5 1,000ths. So anyway, rather than make you see me write a horrible fraction every time there, I'm just going to go ahead and use those decimal approximations. Sometimes you do that, okay? All right. Once we got to that point, then here's what our u sub t looks like. And then our u sub t prime gets really messy. But once you've got those two things, you can plug in the t equals 0 for u of 0. You end up with a C1 plus this point 0004. Since that needs to be equal to 1/6, because the setup we had here, let me jump back over here, the system was being stretched 2 units and then released. So that's where the 1/6 came from. So that, if you're used to talking about 1/6 is 0.166666666 forever, then we just need to subtract 0.0004 from it, so you get approximately 0.1663. Okay. Then once you get a value for that and you plug in for the other portion, you'll get a messy thing that's supposed to be equal to 0, and you can figure out then what the C2 actually needs to be, and it turns out to be super duper small. So hope I got those numbers right there. So that says that our u of t that we've got on this looks like so. And you undoubtedly look at that and say, gosh, I wonder what's really going on with that. Well, what it really says is that this portion here is a vibration that will continue forever, but this portion here is a vibration that will disappear over time. So we end up with a very small sort of reaction happening as t goes off to infinity. That happens to be in harmonic with the vibration that we're talking about, but then the damping effect that we got here is actually going to damp everything else down. And I have a phone call that I'm not going to take, so, or maybe I am. Hang on. Okay, apologies. What else can go wrong, right? Okay. So that was that. Okay, so our last sort of example here is going to be dealing with something where you've got an on-off switch, right? And I purposely tried to make this one not be horrifyingly complicated, but it is. So the setup we've got this time, 4-pound mass stretches the spring 2 inches, system has a viscous resistance, and the system is at equilibrium. That means that u of 0 and u prime of 0 both turn out to be 0, okay? And at t equals 4, we have a constant force of 3 pounds being applied. And I am spotting that I have forgotten to put the 3 in here anywhere. Okay, well, then I am going to handle it the other way and say it is a force of 1 pound. Yay. Okay. So we come along with the setup that we did before, and we'll have the same homogeneous portion of it, but this H4 here, which just means you have a force for t greater than 1, you have a force of 1 that's pushing stuff down. So in the notion of looking at it with a spring, maybe somebody has turned on a very powerful fan that blows the spring down with a force of 1 pound, or a jet of water, or something that would make this happen. That's not realistic. It should be like a vibration or something, but I didn't want to make the algebra of this any worse than it already was going to be. Okay. So the setup that we have here does not lend itself to what we've done in the past. We cannot tackle it with undetermined coefficients because there is not an annihilator function for one of these unit step functions. It's just there isn't one because the annihilator functions are set up for things that are differentiable, and the unit step function isn't differentiable. So what do? Laplace transforms, okay? So we are going to do the Laplace transform of everything in sight here, keeping in mind that u of 0 and u prime of 0 are both 0, okay? So first thing to do is this Laplace transform here. Gosh, why did I leave the 1/8 over there? I don't know. Yeah. All right, so the 1/8 u double prime, the Laplace transform of u double prime, I've looked up in a table, is going to be s squared times the u, and then minus s times u of 0, and then minus 1 times the u prime of 0, okay? And then we'll do the Laplace transform of u prime, which is just going to be s times u, and then minus 1 times u of 0. Laplace transform of little u will just abbreviate with a capital U. And then the Laplace transform for the unit step function at t equals 4 is e to the minus 4s over s. Okay? So once we've got everything transformed, that's when the magic happens. Magic, not so much. Algebra is what we're doing. Seems like magic some days. But we've got all the things with zeros just vanish. And now the cap U has 1/8 s squared plus 2s plus 24 as our as factors we got here. So what we're going to do is to take and divide both sides by that. And that means that our e to the minus 4s, in addition to being divided by s, now is divided by this thing here. And that I don't like writing a fraction inside of a fraction. So I just went and multiplied everything by 8 on the bottom and put an 8 at the top. Okay. So we're going to just look at this portion and then we'll put that back in when we need to. So looking at that portion, we do a partial fraction decomposition. So an a over s, and then we'll say bs plus c over this quadratic. Now, you might say, man, I don't want to do that. Because you may be used to getting quadratics that you can factor here. But if you check, that one doesn't factor. So that it is what is referred to as an irreducible quadratic. So we have to use this particular form for it. If it was factorable, then we would just have a over s plus b over something else and plus c over something else, you know, and that would be super sweet. But of course, things didn't work out quite so nicely. So if you go ahead and multiply both sides by that denominator, then you'll have a times this irreducible quadratic and bs plus c times this s. Now, depending on who you had for Calc 2, you may have been trained, plug in a bunch of values for s at this point. And that totally works most of the time. In this particular case, it's easier to go the other route. If I collect together all of my s squares, I can see that there's going to be an as squared and a bs squared, but nothing else. So that means I've got a plus b times s squared. Similarly, 16a plus c for the s and 192a for the constant. Now, because of the fact that these are two polynomials that have to be the same for every value of s, then this has these polynomials that are on either side have to have the same coefficients. And that means that this 192a has got to be equal to 8. And that gives us a value for a. And then the 16a plus c has got to be equal to 0 because there's no s's over there. And that gives us a value for the c. And then a plus b has to be 0 because there were no s squareds over there. And that gives us a value for b. Yay, we've got it all, right? So now we can say that our capital U is 1/24, that's the a, plus negative 1/24 s, and then minus 23 there for the b and the c. So breaking that apart, I can put the 1/24 e to the minus 4 s over s, which I can look back at my Laplace transforms table and see what that was the Laplace transform of. Okay, and so that's one of the bits that we need to do here. Okay, where was I? Oh, right. So then this piece here, I look for something similar to it, and I really need to have all of this factored out. So I go ahead and complete the square. I would have s plus 8 quantity squared, and then plus 128 left over there, which is really the square of 8 root 2. So I look around and I find out that there's a form that has an s minus a downstairs and then a b squared, but it needs an s minus a upstairs as well. So when I factored out the minus 1/24 there, I would have ended up with a minus 1/24 at the front, and then dividing out, this minus 2/3 actually becomes not 2/3, but rather 16. I don't need the whole 16, so I just kick it over and do something else with it at the end, all right? But so now I have minus 1/24. That's going to be just a coefficient here. This mess here is the Laplace transform of e to the minus 8t cosine 8 root 2t, okay? And then the t minus 4 has to do with, in the table, if you've got a unit step function that has a certain value it turns on at, then you have to replace t with t minus that value in the part where you're inverse Laplace transforming it, okay? Well, the leftover piece that I had over here, I had an 8. And so you're probably super surprised to see the 8 root 2 sitting there. And what I actually did or had to do was, since that 128 was there, which is really 8 root 2 squared, but the form of this in the table had s minus a quantity squared plus b squared, and it had a b up top. So I needed an 8 root 2, so I just multiplied and divided by it here in order to get what I needed, okay? And that is the Laplace transform of this e to the minus 8t sine of 8 root 2t. And then because we've got this e to the minus 4s going on, that's going to connect all this with a unit step function that happens at t equals 4. And that means we have to replace the t's with t minus 4s. That is, I think the technical term is a god-awful mess. So anyway, though, taking a look at this whole long string of stuff here, you can see there's a 1/24 that's a factor of the whole thing. So let's put that out front. There's an h4 that's a factor of the whole thing. Put that out front. Once you do that, then you can see that we've got a 1 here. And then you can see in this piece, you've got the e to the minus 8 t minus 4 stuff. And that appears in this as well. So we'll factor that out. And we'll have a cosine and minus the 1 root 2 times a sine. Okay. So what this actually says is that the function that would be telling you your displacement, maybe I should actually draw a little piece of it here. So the function that is giving you your displacement would be 0 up until you get to this t equals 4. And then it would have this sudden switch on to make a function that looks like all this. And so it looks like, I probably don't have a very good picture of it here, but it probably looks like it does something like this. Okay, so the sudden switch on will make it go away from the equilibrium, but the damping will eventually drive it back. All right. So those are tremendously fun, I know. The best thing that you can do with them is to look at some examples I've worked, look at some examples in your textbook, look at some examples online, and work some examples. I have not written the examples for you. I will have to do that this evening. So anyway, I will see you in class, and we'll spend time on this, and you'll ask questions, and we'll work our way through it. Okay? You get it.